Good to see you're here. That's good. So welcome everybody. April cab call. Should be a fun one. We've got presentation a little bit later from Emily Casey on the current state of cloud native build packs in Paketo. That's very cool. Also, shortly thereafter, conveniently, Ram and Shedrack are running a live stream this morning at 9:30 a.m. PDT on cloud native CI/CD pipelines on Kubernetes with Tecton and Paketo. So that's topically relevant. Aside from that, Cloud Foundry Foundation updates, Summit registration going quite well. There's a couple hundred registrations already, which is nice. The CFP closes in 1 month on May 21st. So good time to, if you haven't put together something, it's a good time to start thinking about that. And voting for track co-chairs, that closes on Monday. And let me put a link to the, put a link in the chat here for everyone who has not voted for that yet. That's just right to the Survey Monkey voting there. And I'll also put the link to the live stream at 9:30 today. Here. It's a long link. Yeah, so that's all I've got from the foundation. So I guess we can move into PMC updates. Eric, you want to run down some app runtime updates?
Yeah, happy to, Chris. Thanks. Yeah, just a few highlights from the past month or so across the app runtime teams. Continued updates from the integration teams. I've had a minor update on CF deployment from Relent to 16.11.0. And then another major release of CF Fricates. I believe they had to add some certificate properties related to injecting the instance index into the application pods that required the major version bump. And then kubectf's been doing some work. I know a little while ago they had removed the CC mode that updates the app deployments, but they're reintroducing that after understanding how it fits into that set of CC jobs. And then they're also doing some things that improve the operation of the log cache job to be within its memory limit inside the containers. I think some of that is depending on some work in the GoCigar library, kind of in the Bosch realm there. Across some of the component teams, I know Cappy's been doing some work on app manifest diffs for setting those app manifests server side and having them apply. And then Irene's been doing some really interesting work. They've been filling in some gaps that they've had between their CRD representation of their LRP resource and the REST APIs that had manipulated those before. And then they're planning on starting some work to explore the consequences of running apps as deployments instead of stateful sets. So see exactly what we might need to change to accommodate that mode of running apps. They've also been doing some work to move their backlog and Icebox into GitHub projects from trackers. So I dropped in a link to that if anyone's curious about how that's going or even wants to see things that they'd be interested in contributing to there. Then a couple other updates around networking. The networking team, I think we've mentioned in the past, there's been some issues with starting in Go 115 around a stricter validation of metadata in certificates. So they've been building the Go router to operate in the more permissive mode where it doesn't need to have the host name show up strictly in a DNS SAN in a certificate that the Go router is interacting with. It's okay for it to be present in the common name, but they're now turning that off. And unfortunately, it's a compile time thing, not a runtime thing. So there's not an option to switch back and forth. But we've been warning about this for a while. So hopefully at this point, certainly all the internal certificates have been updated to have that metadata in the right place. So this might just be an issue for any client certificates that are interacting directly with the Go router. They've also been fixing some bugs around, I think, TCP router port allocations, and then some cases where there's some issues with the policy server when it's running against a MySQL database. And then finally, HA Proxy has, they've had another minor update in their Bosch release. I think doing some fixes primarily to accommodate running on the bionic stem cells where there's only Python 3 available. So anyway, those are a few updates. I'm happy to field any questions before we move on to the main show.
All right. No questions for Eric. Do we have anyone from the Bosch team here today? Updates on that? It doesn't look like it. Okay. As far as extensions, I don't have any significant updates. Of course, Paketo and Build Packs being an extension will be kind of the main feature today. So we got that going on. Is there anything else anyone wants to bring up or talk about before we move on to Paketo and Build Packs?
I have one question. Oh, sorry, it's Stefan from SAP.
Hey, Stefan.
There's one project called Cloud Foundry Community CF Python Client, and we did some contributions in the past and also have some one PR open. And the question in our team came up, what is actually the contribution model for this Cloud Foundry Community project? Is there any way we could, let's say, bring our contributions better in, or we would be willing to invest here a bit? With whom should I talk?
So the Cloud Foundry, I'm not familiar with that project, but the Cloud Foundry community, it's in that GitHub org?
It's in the GitHub org Cloud Foundry community, right?
Okay, yeah. So that's kind of a loosely organized community. I know that Dr. Nick from Stark and Wayne started that a long time ago. So as far as, cool, thanks. CF Python client.
I think it's the CF API client that is also widely used and referenced for.
Right. Yeah, I don't know if there's any official contribution guidelines for the Cloud Foundry community org. CFF doesn't really manage that, but Norm or Tyler, do you all know what the best plan is for getting pull requests and attention on that? I don't know that particular.
Stefan, just let me know and I will make sure things get merged in. It's usually when we see activity, we try to do.
Yeah, we have one request that hurts us a bit regarding logging. That's why I'm asking.
Okay.
A minor change, nothing revolutionary, but would help us in debugging.
I'll go ahead and get that merged in for you.
Cool. But again, if it's possible, let's say, or if you're interested in a more deeper cooperation here, or if you think another contributor would make sense, etc., then we would have an interest here also to, let's say, broaden the V3 coverage and things like that. So because we use it heavily, and
I'll talk to Dr. Nick and a couple other people, and we'll probably just add you as a contributor. Does that make it easier for you?
Yeah, cool. Thanks.
Okay.
Great. Thanks, Norm. Thanks, Steph.
Oh, and one other thing I wanted to mention, a couple of weeks ago, some of us had a document around the vision for CF on Kubernetes that we published on CF Dev, and we've been soliciting comments on for alignment with you all in the broader community. So we've been having some great discussion on the document itself, and then we had also a nice synchronous discussion yesterday in the morning Pacific time, afternoon in Europe, around some of the comments on that. So we're planning on continuing that at the next CF for Kate SIG call in about 2 weeks. I believe that's on May 4th. But certainly if you want to, any of you are interested in commenting on that doc or participating in that discussion, you're very welcome to. I'll drop a link into that document as well.
Yeah, the CF for Kate's SIG call yesterday was really informative. I don't think the video for that's been published yet, but if you check probably later in the day, CF for Kate's Slack channel, there'll be a link to that video. So if you want to catch up on that conversation, you can. All right. Any other last bits of business? All right. Emily, thank you so much for joining us. I'll give the floor to you.
Thanks for inviting me. Happy to be here. Let me share my screen here. Okay. Everyone see the slide deck?
Yeah.
Great. Okay. Oh, we probably want to go back to the beginning of it, huh? It's usually a good place to start. Okay. So my name is Emily Casey, and I'm here today to talk to you all about Cloud Native Build Packs and Paketo, sort of remind everyone of what our high-level goals are and tell you how we're progressing towards meeting those goals. So I work for VMware. I'm a core team member on the Cloud Native Build Packs project and on the Paketo steering committee. And I work with the build tools at VMware. So usually when I talk to people about Cloud Native Build Packs or Paketo, we start off with a comparison to Docker files, because this is the common touch point across the ecosystem. People associate container images with Docker files. And it's really hard to create a Docker file well that builds your application in a robust way and keeps it up to date. But I'm going to omit that whole segment of the typical build packs presentation because you're all here on a Cloud Foundry call because you already know that. Like you're familiar with the day two benefits of a build pack driven ecosystem. So let's jump right into build pack history instead. Heroku originally invented the concept of build packs. At the time, they weren't called V1 build packs, they were just build packs. At Cloud Foundry, we thought that was a pretty good idea and we borrowed it. And the two specs from that point drifted such that there were Heroku build packs and Cloud Foundry build packs, and they were not interoperable with between the systems. So we came together a couple of years ago, a couple employees from Pivotal and a couple folks from Heroku. We decided that the build pack spec needed an update for the modern era, and we founded the Cloud Native Build Packs project and started it as a sandbox project in the CNCF. So let's talk about build packs in Cloud Foundry. These are going to be things you all are familiar with. Build packs receive application source code or an artifact, like in the Java case, usually a jar. They generate a droplet or slug, which is a TGZ containing the application and its runtime dependencies. And then it's the platform's job to create a container that runs this droplet. So it creates a container from the base image or rootfs, streams in the droplet, and starts your application. So there are a lot of really good things about build packs in Cloud Foundry. They raised the value line so application developers can focus on writing their application code instead of spending a lot of time reinventing the wheel in the DevOps space. They provide a lot of security guarantees, so your dependencies are always up to date. As long as you're installing the latest build packs, the build packs will keep your runtime dependencies up to date. If you're installing the latest rootfs, any CVEs in your operating system packages are rolled out automatically. So things that were a big problem for the rest of the industry, like Heartbleed, for example, to patch that for an entire CF instance, all you have to do is upload a new rootfs and every application is updated and rolled forward. They produce consistent results and they're very robust. Folks have been using these for a lot of years, and we've run into every wall that a person could run into containerizing a lot of these typical applications. And we've developed a lot of best practices that now folks can just consume instead of reinventing. Some of the cons, which have been a bit more brief here because we're going to dive into them more in detail, are platform portability. So can you run the artifact that's generated somewhere else? The getting started on ramp experience, the speed of developing in the inner loop So how can I iterate on changes? Modularity of build packs. It can be a bit hard to, because build packs were originally monolithic, it could be hard to inject a small change or a small piece of logic or switch out a piece of logic. Visibility into what's going on in the build process. There are some edges around performance that could probably be improved. And finally, ubiquity. So folks in CF and Heroku are familiar with build packs, but there's an education burden when you're bringing folks onto the platform. It's a new model that needs to be explained to people. So the goal of cloud native build packs was to keep all the good stuff in V2 build packs because we couldn't imagine a world without it, while addressing some of these drawbacks. We want to bring this to a wider audience and hopefully make it an industry standard. So it's not just a piece of the Cloud Foundry platform. It is a standard for builds that is familiar to folks across the industry. That's our big high-level goal. So starting with platform portability, in V2 build packs for CF, the build packs generate a droplet. So in order to run it, you need a platform that knows what a droplet is and what a rootfs is, and therefore how to start things up. The lingua franca of most platforms these days is the OCI image. So one of the first things we did in cloud native build packs was we were certain that the output of the build had to be an OCI image, not a droplet, so that it could be runnable by any container runtime and any container scheduler orchestrating that runtime. So Kate, Docker, Diego, Containerd, Nomad. Once you've moved from creating a droplet to creating an OCI image, then the world opens up for the possibilities of how you could use that output and how you could move it and promote it between systems. The on-ramp for V2 build packs in CF can be a bit tricky. As you all know, deploying your first CF instance on day one isn't the easiest thing for new users. And to really try out build packs, you require an instance of CF to get started. Or you can push to Heroku, but again, they're using a slightly different specification and different build packs. For a while, PCF Dev helped a bit with this, but the startup time for PCF Dev has gotten slower as Cloud Foundry has grown. And the demands of running all of Cloud Foundry in a single VM are extensive at this point. With cloud native build packs, you can download a tool provided by the project called the Pack CLI. Use Docker on your local workstation. And this provides a really easy way for folks who are curious about the project to try it out and run a build without having to have previously committed to installing a larger platform or have to learn about a larger ecosystem. Looking into the inner loop, it can be hard to iterate on changes in your code as an application developer using build packs and CF and see them run in a prod-like container. So one of the promises of build packs is that you don't have to do the work of figuring out how to set up your environment to get your application to run. Like I push it and it just runs. And that works well until I want a tighter inner loop. So I want to, edit a couple lines of code and then see those changes live and test them out. Because you're waiting for an entire upload, staging, droplet creation run in CF, that can be slow. So you can either adapt to that and use it despite the fact that it's slow, or sort of reinvent the steps that are necessary to do this locally without the help of the build packs, which is then sort of going back on our promise that you don't need to worry about how it runs. In cloud native build packs, this is still a work in progress. So I've highlighted things in cloud native build packs that I think are areas that we still need to focus on improving in order to meet our future goals. So the pack plus Docker workflow makes this inner loop quick iteration a bit faster. but we don't think it's fast enough. So one of our goals for this year is to introduce a develop API that would allow users to update a running container with small diffs. So we'll create a build system that looks for changes in the application code and reruns a portion of the build and then streams the changes in and restarts the container. And we think that this will provide a better workflow for developers who we're trying to test out changes, but want to see them running in a prod-like container to ensure that they're working correctly. In terms of modularity, the original CF build packs are pretty monolithic. So I spent a couple months maintaining the Java build packs, and the way folks typically modify the Java build pack is to create a fork of the entire build pack and modify the 1 or 2 things that they'd like to change, and then keep that fork to date for a long time. In cloud native build pack land, there are things called composite build packs that are made up of smaller component build packs. And you can add, remove, or replace a component in this larger build pack system that allows for more modularity. So build packs that used to be, the Java build pack are now broken down into smaller single responsibility build packs. We feel really good about how build pack composition works and the things it enables. In the project right now, I don't think we feel great about the UX for this, like how people add, remove, and replace build packs. We think the fundamentals of the architecture are in a good place, but we need to do more work to make it easy to perform these operations. So diving into the modularity a bit more, because I think it can be helpful to see an example of a modular build pack. So if we take the Paketo Java build pack, in Cloud Foundry, this would be it. It's the Java build pack. In Paketo, it is composed of a series of component build packs. So we have one build pack that installs CA certs. We have the Bellsoft Liberica build pack that can install JDKs and JREs. We have a variety of build system build packs. So I put Gradle here. All of the build packs in here can't fit on the slides. These are just examples, but there's Maven, SBT, LineEngine. There's like a variety of build system build packs that exist in our Java build pack, or you could compose into your own build pack. There are build packs that know how to launch particular types of applications, like a build pack that contributes a start command for an executable jar, along with all of the tuning that goes along with launching it correctly. We have Apache Tomcat build pack. We have build packs that know about specific types of applications. Like we have the Spring Boot build pack that will look at the version of Spring Boot that's in your application, add some metadata to the outside of the image so you can inspect it, maybe do a little bit of tuning on the application. So it says, oh, I know this is a reactive app. I'm going to reduce the number of threads. So we have modular build packs like that that know how to tune and annotate an image when it's using a particular technology. And then we have build packs that provide integrations for APM systems like Google Stackdriver, Azure Application Insights, and build packs that do pretty generic things. Like we have an image labels build pack that would allow any user to apply any arbitrary image label to the outside of their image. So thinking about how this architecture affects you as a user, you can imagine that if you're a big Azure user, you might want to swap out the Bellsoft Liberica build pack with a Azul Zulu build pack. So you get a different JDK and JRE. Down here, I've taken out the Google Stackdriver build pack because I know everyone using this wants to use Azure Application Insights because this is an Azure build pack. So you can, by adding, removing, replacing components, you can compose your own vision of what the ideal Java build pack would be. This happens to be a build pack that Paketo provides. We have an Azure flavor of the Java build pack where we've remixed our own components, but as you can imagine, you could do this yourself, right? So maybe you want the Amazon Corretto build pack. You've written your own New Relic integration that you'd like to stick at the end here. You can see how this modularity allows folks to design a build system in a more intuitive way. And then you can obviously take components of these and use them in a totally different context. So the CA search build pack and the image labels build pack are not specific to Java or Paketo at all, really. So you could have a totally different system that runs a build pack for running functions written in Rust, but maybe you want to stick these two components that Paketo creates in your build pack to get these features. Moving into another pain point that we have seen in our experience running build packs in CF that we would like to improve in the world of cloud native build packs is visibility into what's happening in the build. Folks sometimes talk about how build packs are too magic. And magic is a good word and a bad word. To some extent, people want magic. They would like it to just work, and they would like to not have to put a lot of effort into getting it to work, right? So magic can be really good. But we found in our experience that it's not always true, that people are okay, the famous haiku, here's my application, just run it in the cloud for me, I don't care how. People don't want to be forced to care how, but they want to be able to learn how or tweak how when they find a situation that they care about it. So we found that folks both want more visibility into what's happening in their build pack, the build process itself, and visibility into the output. So they want to know exactly what we've installed in this image so they can make sure it meets their open source licensing requirements and audit requirements and figure out which images have CVEs in them. So this is a problem we've taken really seriously when architecting cloud native build packs. We have created a bill of materials, which gets applied as an image label to every image created by cloud native build packs. So as the build packs contribute things to the image, they add descriptions of what they've contributed to the bill of materials. And at the end, you should get a bill of materials describing everything in your image. We're still doing some work to improve that. So we'd like to, right now this works for build pack provided dependencies, and there's a different format where you can get the dependencies that came on the base image. We're working on creating everything in one place that's totally comprehensive. We're thinking a lot about the format of this bill of materials. Right now it's a custom format, but do we want to be moving to SPDX or Cyclone DX or something that can more easily integrate with other tools in the ecosystem? And back to our topic of magic, cloud native build packs are still a little magic. The complaint that folks don't know exactly what the build system is doing is not a totally solved problem yet. And we've just started looking into ways to improve this, either by creating better visualizations of the build, creating interactive builds where you could hijack a particular component build pack or run them one at a time. So this is a goal that is in progress, but we think we could do even better. In terms of performance, there are a couple ways that V2 build packs for CF are slightly inefficient. So they end up storing many copies of the same artifact and using a lot of storage. So if you have thousands of Java apps and each one of those Java apps has a JRE in it, because of the way we handle droplets, you're going to end up with thousands of copies of the same JRE that you're paying rent on in your storage location. And as you stream these droplets to the Diego cells that run your apps, you're going to end up with thousands of copies of the same JRE on those cells, and you're going to need to re-download the whole JRE again every time you push a new application, even if it's already there. It's not terribly slow, but it can be a little bit slower than it should be if nothing has changed. In Cloud Native Build Packs land, we've been trying to use the layers in the OCI image in an intelligent way to reduce duplication and unnecessary data transfer. So if you're building an app with the Paketo Java build pack and it has a certain JRE in it, that layer is going to look identical to any other app built with that build pack using the same JRE. So you only need one copy of it in the registry, and you only need one copy of it on the worker node. And this is a big deal in terms of data transfer and data storage. Also, as the OCI image is built by build packs, only layers that change need to be rebuilt and transferred. So build packs can opt into using a layer that's already on the registry directly. So this means that you only need to wait for the parts of your system that have changed to rebuild and upload. You're never going to wait for the same JRE to upload to storage again because you changed a single app file. We can just reuse that JRE layer, and we've broken up your application into what we call slices, which are layers where we group things that we think change in unison together. So you're going to get one tiny layer upload that contains your change instead of rebuild and re-upload of the whole system. There are still areas where we could be improving performance. Cloud Native Build Packs is great on a rebuild, but in the case where you're not using an offline version of a build pack, we do have a bit of a performance problem on the first build, where let's say I'm building 10 different Java apps. It's still going to go ahead and download that JRE 10 times, once for the first build of each artifact. And that feels like an unnecessary performance penalty to us. So we're looking into better ways to handle asset caching so that even that first build can be really fast if you're using components that you've used before and they should be available to you. Ubiquity. So we're all familiar with CF build packs. Cloud Foundry and Heroku users are very familiar with the concept of build packs. But for folks who haven't used either one of these platforms, most people are not deeply familiar with build packs. And therefore, if you want to get someone excited about Cloud Foundry, you have the burden of education of teaching them about this whole new build system and, walking them through concerns and talking about the potential upsides. The fact that this technology is specific to a couple platforms puts a burden on the providers of those platforms to do a lot of education about the technology. Our goal for Cloud Native Build Packs is to become a standard and be used more broadly, to still be a core component of Cloud Foundry, but to be a component of platforms and CI tools and a variety of integrations so that it's a familiar concept and the benefits and drawbacks of using build packs are more widely known. And to that extent, we've been pretty successful so far. The project is now in the incubation stage in the CNCF and has been adopted by a range of cloud providers that are building platforms, by companies that are using it to build their own images as end users, by folks that want to provide build packs. We still have a ways to go. We feel really good about the progress we've made so far, but average developers are still unfamiliar with build packs, so there's more work to do here. So diving into this a bit deeper, on the left, you can see an incomplete list of platforms that have adopted build packs, like incorporated a cloud native build pack build as a feature in their platform, and sort of a graphic that can help us understand more what incubating in the CNCF means. So we are past the stage where we're getting the early adopters, and we're moving into the phase where we would consider our users the early majority, and hopefully we'll be continuing to grow from here. So our big goal is not just to build a great tool, it is to build an ecosystem. And to understand how that shaped the project, I'm going to dive into the architecture a little bit. So the Cloud Native Build Packs project at its core is a specification project. In that specification, we've defined two APIs, a build pack API and a platform API. And we ship a component that's used by all of the adopters that understands both of those APIs, called the lifecycle. So the build pack API describes what contract a build pack needs to meet in order to participate in the system. And the lifecycle exposes an API to platforms that then allow platforms more easily, without understanding the details of how build packs run or how their output is transformed into an image, to offer a cloud native build experience by driving the lifecycle with the platform API. So lifecycle is a cloud native build packs component that we ship. You could implement your own by implementing the specifications, but that's generally not how it's done. Most people are just using our lifecycle. But there are a variety of folks who have implemented either build packs or platforms to participate in this ecosystem. So the first platform that folks usually are introduced to is the Packs CLI. This platform is actually provided by the project itself. We thought it was important to have a smooth local getting started experience where people could try out build packs, and a CLI tool is great for that. But since then, like, interesting developments that we didn't foresee have allowed this technology to reach more users. So the Spring Boot team was pretty excited about cloud native build packs. And also the teams at Spring that are building native images, like Java native images, where the build is a difficult process, wanted to provide a more standard experience for how to get a container that implements all of the best practices for running Spring. So they implemented a platform that drives the lifecycle using the platform API, and it's a Gradle and Maven plugin. So because we made the specification the first class concept, the Spring Boot team was able to solve a problem that their users had, and at the same time create an experience that was really familiar and native and great for Java developers, and has really expanded the ecosystem of folks using cloud native build packs. Another platform of note is Kpack, which runs cloud native build packs builds in Kubernetes in a fully declarative way. So whereas Pack is a great platform for getting started, Kpack is very intuitive for folks who are familiar with K8s, and it is great for running images building images at scale. So because it's using the declarative engine in K8s, it will rebuild your image when a build pack has changed with new dependencies, when a new base image comes out. So you just sort of describe what you want your images to look like, and it's constantly spitting out builds. So we can look at a slightly outdated diagram here, but you take your image, you give it a builder, which contains a list of build packs to build, and you give it some secrets and some source code, and anytime the latest build is out of date, either because you got a new base image or there's an update to your source code, it spits out a new build, which puts a new image in the container registry. And you get this declarative engine for building images that are always secure and always the latest. And then you can compose even building on top of other platforms. So CF for K8s is using KPack to create an entire PaaS experience. So while KPack is a great K8s native build experience, we all love the CF push experience. So something like CF for K8s can use KPack as a build system to create an even higher level platform that meets the needs of different types of users. And this works across the board. So there's a Circle CI orb that uses the Pack CLI. So we're seeing this ecosystem of tools that build on tools start to emerge, and that was our goal. And it seems like that piece of how we saw the ecosystem evolving is on track. On the other side here, we have build pack implementers. So Paketo is the Cloud Foundry Foundation implementations of the Cloud Native Build Packs, Build Pack API, but we are not the only ones who've written build packs. Google has build packs, Heroku has build packs. There are VMware Tanzu build packs. We know of end users who are doing some combination of all of these, like using Paketo build packs, but maybe they've written one for themselves. We have folks who are looking into building build packs specifically for creating functions. So this is another area where you can inject in. And because of the specification, everyone gets to worry about just the piece they want. So implementing a build pack is a constrained problem, and someone who wants to extend the build system only needs to worry about solving this problem. Someone who has a vision for a platform and that platform needs a build functionality only needs to worry about this end of the problem, and they can just plug in the Cloud Native Build Packs lifecycle and engine. So to talk about Paketo a little bit more, the goal of Paketo is to provide best-in-class build pack implementations that we hope will become the default for people who are looking to run Cloud Native Build Packs in whatever platform. So we have implementations for all of the most commonly used major language groups, using our experience in CF to predict what will be the most popular languages. They're open source, free to use. We are drawing from years of experience developing the V2 build packs for Cloud Foundry and trying to incorporate new learnings to create new features that are enabled by the Cloud Native Build Pack specification. So just to dive deeper into one build pack, I feel like the Java build pack provides a good example of how we're combining sort of the best of what we've done on CF with new features enabled by the new specification. So a lot of these runtime helpers, things that link your application to the local DNS, the component that calculates memory, stuff that loads, components that load the CA search from the system trust store into your JVM trust store, a component that kills your JVM correctly when it's out of memory, which is really important in a containerized ecosystem. All of these were things we developed for Cloud Foundry that we've now ported over to the Paketo world. And this is why we think Paketo build packs have a real chance of being the best build packs. We have so much experience with all of these little nitty-gritty details that you would need to have the best containerized Java application. We have robust command lines for multiple types of deployments. Again, a lot of this is coming from our experience in Cloud Foundry. And then we're taking advantage of some of these new features. So we're adding the version of boot in an image label. So you could do a query across your whole K8s or CF and figure out exactly what version of Spring Boot is in each application, stuff like that. And then of course, the bill of materials we talked about before, we've put a lot of effort into making this really thorough in the Java build pack, so folks can do things like security audits or open source license gathering, stuff like that. That is a broad overview of where I think we're at with Cloud Foundry and Paketo build packs. And I didn't leave quite as much time as I thought I was going to, but I wanted to leave time for questions because I'm sure y'all have burning thoughts, desires, things that you wished I had talked about that I didn't. Anybody, questions, comments?
And I start with one question. What are my options as a application developer running on a traditional CF deployment with the standard Java build pack in V2? And I'm curious whether my application would actually run also with the new type of build packs on my existing Cloud Foundry landscape.
I think the lightest weight way to start testing that out is with the pack CLI. So one of the nice things with the way the specification works is that it shouldn't matter what platform is orchestrating your build. If you have the same build packs in the same application, you should get a totally identical output. So you can download the pack CLI and pack build and pass it your application, and the image it generates should be the same image as what you would get in CF for Kate or Tanzu build service or a shimmed V3 build pack if we in the future provide that onto Cloud Foundry.
Okay, thanks.
And can you say what you mean by a shimmed V3 build pack?
We've been thinking a lot about migration from V2 to V3 build packs, and there's two ideas that have been floated. I can't make promises about which of them will be implemented, if they'll be implemented, or in what order, but folks are definitely interested in it, and it would involve writing a shim or two shims, one that would allow V2 build packs to run in a V3 system. So it would sit in front of the V2 build packs and make them look like V3 build packs so that any of these new platforms could run the old build packs, and the other shim would work the other way. So it would take our new build packs and make them implement the V3 Cloud Foundry interface.
And to Stefan's question, so we would just treat the output from the current pack CLI as just a Docker image and run it in CF that way?
Yeah, you could CF Docker push it.
Yeah, okay, thanks.
I didn't mention this in the presentation because it's getting a bit into the nitty gritty, but you might be aware that like a rootfs update wouldn't work for something CF Docker pushed into CF, but we've sort of like reimagined what a rootfs looks like in cloud native build packs with an operation called a rebase. So you can swap out the base layers with new base layers using in pack could be the pack rebase command, but a platform like Kpack would just do a rebase if it saw that your base image was out of date. So if you're running these CF Docker push images and you want to update the base image, you could also do that with the pack CLI and then repush them. Anybody else?
I'll jump in with another question. How is your team making the product management decisions of which to prioritize? The V3 build packs, from my perspective at cloud.gov with the potential compliance advantages it would bring, and letting small teams identify outdated dependencies and potentially rebase them would be huge. So I'm kind of hoping you can get it running with the CF push experience sooner rather than later, but I know there's other priorities involved too.
There is a crushing amount of priorities and asks in different directions from different people. So I can't, but there's a lot of interest in making the V3 build packs available to Cloud Foundry users without requiring Cloud Foundry to implement the new API. So I think if we were going to build one of the two shims I talked about, it would be a V3 to V2 shim, probably. Anybody else?
Just want to thank you, Emily, for your talk. It was very good, actually.
Thank you. I'm glad it was useful.
Set the focus of where you guys, where the build pack is going. And my experience with the original Locato was very painful to build things, because you had all these different layers and stuff like that. And you had to use another command. It was making it very difficult to build stuff. So hopefully this new stuff that you're coming up with will simplify it somehow.
Yeah, we don't think we've solved all the problems we aimed to solve yet. I think we do feel good about the fundamental architectural decisions we've made, that we are poised to be able to solve the problems we want to solve.
Is there anything going on with improving the documentation so it'd be easier for people to figure stuff out? I mean, it took me a while to figure out how to get Python to work correctly and stuff like that.
Yeah, we've actually spent a lot of time recently talking about documentation, and have brought in look for help from a designer as well in that area, because it turns out that we might be really good at building build packs, but making a comprehensible and beautiful website is something we are only okay at. So we're trying to get some help in that area as well.
Awesome. Well, thank you so much, Emily, for that very thorough, informative presentation. That was great. And I believe that's probably a wrap. Anyone else have any last minute things they want to bring up? All right. Well, thank you all very much. And thank you again, Emily. And yeah, we'll see you next time.
Thank you all for taking your time to listen, and have a good day.
Thank you, everybody. Thank you.